Recording is on.
Yes.
Okay. Uh, my topic is today about today talk is SmartNIC-Accelerated intrusion detection with nested graph neural network. My name is Dr. Rana Abu Bakar. I did my PhD from Scuola Superiore Sant'Anna, Pisa, and this PhD is basically funded by CNIT. Currently, I am also working in CNIT as a area researcher in the field of hardware accelerated network and services. Uh, Before going to SmartNIC and hardware acceleration, I want to give you a little bit overview of graph neural networks. Like if you can basically assume that graph neural network basically help us in different field of our daily life. Like it will help us in medical. It will also help us to make a knowledge graph, make good information, and also helpful to make a brain or neurons. And if you have to also in medical genes prediction of RNA sequence to help to predict like for example currently they are predicting medicines. And for communication it will give us insights so how our network devices are connected. And in software also in social networks like your social networks in LinkedIn and Facebook, these are basically we can represent by using graph and graph neural networks. It will help us to predict any of this application by help of graph neural network. Currently, we have some problem. We can solve some problem by using graph data. We can basically predict node level predictions. Uh, like for example, in network, we basically see if a node is a malicious or a normal node. We can predict it by using graph data we have. We can also predict the link level prediction, like between, if you can see here, between two red nodes, we can predict the link level, how is link, like for example, this link is suitable for video or not, this link is suitable for medical, or this link is suitable when you are if you are traveling in seaside. In that area we basically also working on this area to predict the uh, some good link for this type of communication. If there are two people, they are sitting there, one is using the video streaming and one want to send a message over WhatsApp, so we will give the preference by this type of communication. So graph level prediction, for example, if we have to predict it by using graph, we can talk about the security firewall. Is this GNN can help the firewall, state of the art firewall or next generation firewalls to protect from attacks. So this type of problem we can solve by the graph data. This is a message passing information, like in graph neural network, we basically provide the information by using an input, and these input are basically the messages from different nodes. Here we can say we have a different nodes are there, and we have a different messages x1, x2, x3 represent to the one. And then we have also another node 2 which have also some message information, and here we have also message information from 3. If I can give you the real example of graph based information, for example, these 5 students are sitting inside the class. So student 1 has the some information, and student 2 has some information, student 3 has some information, and student 5 has some information, and then same as student 4 has some information. So for example, this is the message passing information, and these are the 5 messages. 5% they have 5% has some messages, but they want to convey this message to the teacher. So how they can convey this message to teacher? Maybe they can join to this information to represent, make a representative and send information to the teacher. So these are basically the information they can gather it to the by using a one, and then they basically this is the they gather this information to as a h1, and then they send it to the teacher. This is the message passing information we utilize in graph neural network. And how they can update, they update it like basically when we update this information, there are some problem of overfitting. We will let us see how we can overcome this overfitting with our approach. So now I want to introduce the DPU is DPU mean is data processing unit. So like GPU is basically graphic processing unit. Now this is not a graphic processing unit. This can also solve your problems. But when they started, like this is the meaning of DPU is. But here this is we have to just tell about what the DPU is. Like if you can see on starting, this is a wireless antenna, or you can say this is 5G 6G antenna and connected to the router, which is connected to edge device. This is the whole edge device. In current scenario, without DPU, we have the CPU, GPU, and only NIC there. So if we have to process the packets, so we can use our CPU and GPU to process it, and then our CPU load is should be high. But if we basically, why we are adding here a DPU here, like for the security use case, we don't want to open our CPU and open our GPU or our memory to the packets or the some malicious packets. For example, this is the data processing unit. I already told you, accelerated computing platform for data center infrastructures. So it's built to power AI factories, and also like it give power to a programmable power to a NIC programmable processor. So if you see this small animation, so when packet is arrived, it's passed to the router and then it's passed to the DPU. So in DPU we have a CPU ARM processor, we have graphic processing unit inside the same system on chip, and then we have a ASIC there, and then we also have the NIC, like we receive from the NIC and then we process it. And if we have a firewall here, we can easily mitigate or block this type of attack. Here we have also connection between this node and the DPU if we have to send some normal packet toward the host device. Here I want to give you a little bit more introduction of DPU. In DPU, we have three paths. The first path is, I already told you in the previous figure, we have a ASIC chip. So here, this is the E hardware switch, which is basically connected to the port, two physical ports, P0 and P1. And these are connected to by using ASIC chip. This is our basically ultra fast path. I will tell you later on how this is ultra fast path is. But here ultra fast path, like we have very limited functionality, like we have some fixed functions, like where we can utilize, for example, a packet is arrived and we have some function aligned to this packet, and we match this packet with this specific function. It will basically receive here and it forward to port 1 without involving the ARM processor and without involving the host, like here we mentioned what CPU and GPU is. And then we have the ARM processor, like if we need to process some packets, like for example, we want to make a 5 tuples based on source IP, source port, destination IP, destination port, and protocol. We make a flow by using these 5 tuples. So here we can involve this fast path to make the flow ID. Like first time a packet is arrived with these 5 tuples, we send it to the ARM, and then we have the basically ID, and we send this ID to the E hardware switch. If a new packet is arrived match with this ID, it should goes to the hardware switch. So this is we involve only the first packet is basically to the ARM. The next packet goes to the port 0 to port 1, or even we have to send to the host. And slow path, where we need to process some we need a huge computational cost, like huge GPU or the memory, so we can utilize the host path. So these are the three paths available inside this DPU and the SmartNIC. Why we include GNN in the DPU is, currently, if we can talk about the state of the art, we have FPGA, like, and we have also P4 based processing. So we basically receive the packet flow here, and then we have to send to the FPGA pipeline. So when we send it to the FPGA pipeline, basically we introduce the latency here. This is the latency we introduce here if we have a FPGA based solution. If we have a recent state of the art tensor core based GPUs, we have basically receive the packet flow, we parse it by using inside the NIC, and then we extract some feature and send it to the GPU. So this orange line basically show also the latency here. Uh, Actually, this device or a switch or the server don't have the capacity to process the packet and basically like parse and deparse and then insert to the egress pipeline. So it has to send these to the GPU for the prediction. This is our approach where we have a system on chip. We basically parse the packets and then we have a GPU inside it, which is connected to the NVLink connection between the NIC and the GPU. We parse it and then we basically enforce our policies and then forward this packet. Here, in this method, the GNN model basically fully implemented inside the DPU, like fully pipeline is basically inside the DPU. In these cases, this is a limited data rate because they have a PCI Express connection between GPU. Here we have also a PCI Express uh, bottleneck, and also same here. So now the motivation behind this work is if we talk about nested GNN, network tracks are increased. We have seen in the Cloudflare reports, it's reached to 4.8 billion packets per second floods and 7.3 terabytes. In quarter four, it's reached 31 terabytes something. So you see almost 4x increased in 1 quarter. In like 2024 quarter four, it has 31 terabytes. Traditional ideas and flat CNN fail to capture basically hierarchical pattern of these attacks, and we need a scalable real-time intrusion detection system for 100G, 200G, 400G, even the 800G network traffic. And if we have currently SmartNIC is available for SmartNIC, it's Bluefield 4 with 800G, it's available. But in our lab, we have a 400G gigabits of Bluefield 3 available, where we implemented this nested GNN real-time hierarchical intrusion detection system. Our key idea is basically here to utilize Dock SDK. What is Dock SDK? This is the SDK is basically provided by NVIDIA to program to utilize efficiently these three paths. Already showed you in the previous slide. So if you want to utilize these previous path, these are path efficiently, you have to utilize Dock SDK. Otherwise, these fixed functions and some function for the ARM not available without using this SDK. So we perform packet parsing, flow state updates, and graph construction and GNN inference inside the GPU memory. And this is basically inside the basically data path is inside the GPU pipeline without involving the CPU ARM. Only the first packet we involve the ARM processor to make the flow tracking, like initialization or rule updates are depend on the ARM processor. System architecture basically it's consist of NIC, GPU, and CPU. NIC is Bluefield DPU where we have the flow, and the GPU is also embedded on the same system on chip. We utilize the GPU NetIO RxQs. This is GPU NetIO is the library. We basically build RxQs on UDP, TCP, ICMP, and we utilize the Coda kernel for packet processing. GPU resident flow table are also sit on the GPU memory, and we build a graph on this flow table entries, and then basically we also make a GNN inference on base of this flow table. Docker initialization, port initialization, and queues initialization is depend on the CPUs, and this is like operational enforcement flow rule installed. We have two stages. First stage is per packet processing. Like per packet processing is depend on when we have a new packets. Header parsing, we basically parse the header inside the GPU. Flow feature are updates inside the GPU memory, and it's basically and some of lightweight counters are also saved in the GPU memory. And another one is the batch GNN inference. Here, basically, when we have a flow entry of the different flows, then basically we make a GNN by not on each packet, but on batch GNN. And we operate on active flows, like currently what are in and out flows are going on based on these five tuples, and then we basically did this batch GNN inferences periodic based execution. No per packet inference is involved here to save the GPU and save the ARM processor, because we have very limited processor, and we have to save the bottleneck not to send too much request toward to the ARM processor. And if we talk about some existing GNN based IDS issues, like they have a flat GNN which basically cause for the oversmoothing and cannot capture both host level and network level dependencies. It basically costs computational cost is very high, and adversarial structure is also changes. Our GNN has three layer architecture: internal GNN, which basically process the level graph per host per node, and another one is the nested layer, which can help us to make a reduce and merge embeddings, and then extra layer, which basically make a present host to host communication, and make a classification of graph which is based on node to node, and it enable us multi-scale reasoning. It provide us the multi-scale reasoning. This is the architecture of, if we can go more deep on this architecture, we have this inner GNN. Like we have different type of subgraph here. Like for example, these subgraph are represent on sub area. For example, this is sub area of one department where we have a three nodes, A, B, F. And for example, you can also represent it. Already I gave you the example of students in the class and the teacher. So here we have some processes running on node B and some processes running on node F. For example, if I can show you in the this animation, like process 1 to process n is running, then we have basically combined these processes and represented by this red highlighted node, and then it connected to the main graph, and these main graph connected to the outer GNN. Here we have nested GNN, reduce and mean layer, where we basically it will help us to minimize the computational cost, and it will basically also minimize the internal processing of these subgraphs. And on the basis of these, we basically classified the graph and classified the nodes. And these are some results, and F1 result is very good compared to the others. Basically, if we here we basically purely target the hardware, and we have very limited ARM processor, and we have to process almost 400 G traffic, and it almost going to the 94% of F1 score, and weighted F1 per score is also very good compared to the approbation ratio is. On the right side, we have also compare our NGN and GAT based approach, which is basically compared to others. NGNN, GraphSage, and NGN DCN. It's showing a good result in terms of accuracy and F1 score. And why accuracy and F1 score is good? Basically, we keep essential features only which are useful. Basically, we in the mean and sum we reduce some extra features to remove the noise. and it will help us for less over smoothing and better node discrimination. Basically, this data set is collected here. If I can go back in previous stages here, basically we create some nodes which are they have some normal processes and some malicious processes, and same in each subgraph. So this local data set is basically help us to for better node discrimination, and it's basically good for clearing, embedding, and more robust classification for graphs and nodes. So this type of approach not only good for the network security, it can also helpful in the medical field where you have to predict RNA-based sequence and you have to make some cancer cell prediction. You can also predict it by using this approach. These are envelopes, basically what we showed here in GCN and GAT. We showed that in our nested base approach, not double the, like if you have a nested layer, it can enhance the number of flops, but we use some and concatenation approach, which will reduce the flops, and it goes to 2.25 flops. And these are the processing. If we can process CPU only Xeon processor on the server, it's this type of GNN model. It take almost 320 millisecond to pre-process it. If we only utilize the GPU based approach, it's 380 millisecond pre-processing. But we have some issues with the GPU, like so every packet basically goes to the GPU, and we don't have the capacity to make a flow ID or flow tracking by GPU only. If we involve the SmartNIC plus GPU, it's take almost 325.6 milliseconds to process this data, and training course is very limited, 48, and inference time is zero point 0.3 millisecond. So these are some numbers about the computational cost of our approach. If you have any question, I will answer you now. And if you want to get more insights about our model, or to get more insights how we can make it, we will help you, and I will welcome you, your question and your queries and your suggestions.
Yeah, thank you very much, Rana. Um, yes, actually, so maybe I ask first if there is any other questions. I have already some questions, but I don't know if there is any other questions. So please. Okay. Yes. So Zain seems he has one. How large were the files you transferred using DoCATMA? Yeah. So Zain has a question. So the question is, how large basically were the files you transferred using DoCATMA?
Basically, in this approach, we have not utilized the Docker RDMA. This is without RDMA stuff is, but we have another Docker RDMA based application where we use data path acceleration. This is a DPA. In data path acceleration, basically we have very good benchmark. If we want to get some information, then Proki, we will provide you about. We have basically in this approach, we not only consider the large in RDMA. Usually they benchmark the large payload, but we also payload benchmark for the small payloads. So we have very good reports, and I will share with you if you need.
Mhm. So basically, you use DPA.
DPA is another approach. I want to just answer the Jan Froki question. Like he asked about the RDMA stuff, about direct memory access. So there we use data path acceleration. This is another acceleration inside the blue field. So in this work, I have not discussed about any DPA stuff.
Oh,
Like here, I only discuss about GPU, graphical processing unit inside the same system on chip, and the ASIC chip. not about the DPA. DPA is basically it's a RISC-V, look like RISC-V, but it has 256 threads.
Mm,
They use almost 96 66 threads for the congestion control PCC. They have a PCC
mm,
base congestion control where they use these 60 threads,
mm,
and 190 is available for other type of processing.
mm.
So in this work, basically I target data path acceleration DPA.
Yes. Okay, great. And then, I don't know, is there any other questions? Actually, if is there any other questions? So maybe actually I can. I have some questions. So you mentioned, because actually one of them already you answered. So you mentioned the information. It was the DPU. Basically, it was Bluefield tree.
Yes.
Yeah, and then I I see that. So you mentioned about these three approaches that basically we have to we can. Is it like because I remember for the Bluefield 2, for example, we can change the configuration mode. For example, if I remember correctly, embedded mode or like a host mode. Then
Yeah,
based on this mode, then we can have. Is it the same as those modes, or no? Is it other way?
yeah. Like for example, what you are talking about, there are two different modes, almost three different modes. One is DPU mode, which is called embedded. DPU and embedded is the same,
Yeah,
like where you have the ARM processor. Then another mode is NIC mode,
yeah,
which it will convert you as a NIC, network interface card. There is a no more access of the ARM processor. So these are two modes are usually available. Then another mode is zero trust mode, security. This is embedded mode, but here in this mode we don't have information, or we don't have a communication between server and the DPU. This is zero trust.
yeah.
So it is connected on the PCI Express, but it has not give any access to the server. So this is utilized for some security use cases.
Independent. Yeah, but then these three approaches was the basically corresponding to these configurations you mentioned.
In this approach, basically we have the DPU mode. Like our most of work is DPU mode. Like we have to sometime to utilize the server resources. Sometime we have to utilize some DPU resources. We use the DPU mode. But in RDMA approaches, we have not utilized the ARM. We use the NIC mode. So we run our application inside the x86, and we can basically process. And because there we, for example, we are running a graph-based or a weather prediction application, which is very heavy running on the server. So we don't want to go to the ARM processor. So we can basically change DPU as a NIC mode. So we can have the DPU and other processing. But in this task, we utilize the DPU mode.
DPU mode, yeah. And then actually, if you, I mean, you because you have the experience for this like IDS and anomaly detection, so you believe that, for example, for which type of like anomalies it is good. I mean, like the like a GNN.
I didn't understand your question. Maybe you are talking about GNN, GNN. Which type
I mean,
of attack is detected by the GNN? Like
yeah,
GNN is
yeah,
efficient in which type of attack? So,
yes,
in my opinion, currently, if we can think about any flooding in Cloudflare, mostly are SYN flood.
okay,
So, if these are the SYN flood, so in SYN flood we can track the flow. So, tracking of the flow is very GNI is performing super good to track the flow.
mhm,
So, in my opinion, the SYN flood attack or the volumetric attacks are basically easily handled by the GNN.
mhm,
So GNN are good. And also layer 7 attacks, like where we have cross-site scripting, SQL injection scripts. This is called not a high level, like a slow risk or slow level attack. So these are also GNN performing well,
mhm,
like,
okay,
and it's also efficient in smaller devices like ARM processor. you can even build in small devices.
That's not less, yeah. But actually, because as for example, now you don't use ARM, but if you, I mean, like for example, the benefits of having it on the DPU rather than running on the host. I mean, what would be the benefit if you wanted to just share with us? What is the benefits of using? Because some people they said, okay, so we can have like, I mean, apart from this that you said, yeah, maybe the CPU there is just like. High load, don't want to use it for this type of activity, or maybe we don't want it to have like some traffic bring it to the host that we might guess that it's just like malicious traffic, so we don't want to have it there, and then it's better that we process it like in isolated like inside the NIC. But regarding the performance or some other aspect, if you wanted to compare the host and DPU, I mean, what is your like recommendation? So you, I mean, in which case you prefer DPU?
Yeah, for example, in future, we have also talked with NVIDIA. Like in future, they are thinking about this DPU should be fit in inside autonomous vehicles, or should be fit inside the robotics. So there we don't have the x86 machine or a server there. So maybe they have to fit these cards inside these robotics or autonomous vehicles. So in that case, it's good in DPU mode. You have everything. You have ASIC on system on chip. You have a DPA on the same chip. You have a GPU on the same chip. You can perform it. And now they are also building on making the switches. So maybe in future they have a switches where they can install this card. So there should be a DPU mode also can perform very well. So in compared to the HPC side, high performance computing side, like they have currently the NICs inside their clusters. So if they have blue field inside the cluster, just replace their NICs with and like they can basically offload some MPI operations inside the blue field. So blue field 3 has DPA, data path acceleration, so they can parallelly offload. Like MPI is basically good in parallel programming, so they have 190 threads, so they perform operation by using these DPA threads. So parallelly they are running some operations inside the x86, and also they can run something. So they, in my opinion, DPU mode is also perform very well in HPC use case with the MPI.
But then, I mean, for example, like regarding the latency wise, and then if you wanted to use it for something that is we need low latency, I mean, which DPU you suggest? For example, like you suggest Bluefield, or maybe you suggest other one like AMD Pensando. That one basically has a real ASIC, or like other type of DPUs.
Basically, there is another competitor of NVIDIA. Currently, I have only expertise in Bluefield by NVIDIA, because we have in our lab, we don't have Netronome. In Netronome, they have FPGA on the same system on chip. So Netronome perform very well, but they are limited to the bandwidth. So I see they have only 100G. Currently, in clusters or HPC or AI, they have 800G based communication. So this type of network card are not suitable. There are some other card are currently available in the market, but here, like the Bluefield 4, is very useful in low latency. So uh, we have to, like, you, if you have there are some circumstances like where you want to fit it. Also the price factor is very
Yeah, it's
important.
important. Yeah,
Like
price. Yeah.
Metronome card are very expensive compared to the Bluefield, Nvidia Bluefields.
Yes, yes, and probably also the SDK access. Also, that was the another
Yeah, like,
concern.
yeah,
Yes.
they have a very good in Metronome also very good community. Like they are purely working on DPDK stuff. So DPDK is very stronger community, so you can easily find your concern, or you can easily get a help from the community. But here in NVIDIA, they have also a community, but this is official community. They are good in responding on forums. If you have any problem, you can ask on the forum and they can respond to you.
Mm. Okay, great. So thank you very much. Is there any other question? Actually, yes, I'm done with my questions. So, is there any other questions? Thank you very much.
You're welcome.
For answer. Is there any other question? Uh,
About FPGAs. Was 100G on FPGA?
Metronome.
Yeah. Is that like what kind of FPGA is this? Netron? No.
Yeah, there is another DPU. Like this name is Netronome, and they have maximum, as per my understanding and knowledge. But I see 25G, but I see in some reports they have 100G base DPUs. This is a Netronome. Like if you want, I can
And they
give
are
you.
based on FPGAs, right?
Yeah, they based on FPGA. So they have FPGA on the same chip.
Nice.
because yeah, I see that. Yes. Yes. Great. Uh, is there any other questions? Okay. So now I can stop sharing. Thank you very much again, Ran, for a very nice talk. It was very.
Thank you, Masood.
Thank you very much. So I stop sharing now.